Hi, and welcome to Math 232, lecture 2.4, applications of systems of linear equations. This should be a relatively short lecture. There's no new mathematics in this lecture. What this is intended to do is just show you that the solving of systems of linear equations has quite widespread applications in a variety of settings. So what you want to be able to do at the end of this lecture is to understand how to take a problem, and we'll do like a chemistry problem, a network flow problem, an interpolation problem. And what you want to be able to do is take the problem, understand from the problem how to generate the system of linear equations that solves the problem. And then it's just a matter of doing the Gaussian elimination and finding the solution. So the interesting part is actually taking the problem and understanding how to generate the system. But also, because we're sort of relatively new to this, solving the system is also going to be good practice for us here. Okay, so let's just take a look. We've got a bunch of vocabulary. This is just to perhaps, if we're all from a variety of different backgrounds. So some of us are in physics, some in engineering, some in economics, etc. So there's just some vocabulary here to indicate what kind of physical things we're wanting to know about in order to introduce these examples. So read through those and at least understand the very basics of the problem that we're trying to solve. Okay, so the first thing we're going to take a look at is a flow network. So a flow network can represent a whole bunch of things. It's basically some amount of branches, we can maybe call them pipes, and then there's some sort of nodes where more than one branch comes together and stuff flows in there. And we want to understand how the flow through different parts of the network influence or force the flow in other parts of the network. So it could be electricity flowing through wires, liquid flowing through pipes, traffic flowing on roads. I'm sure you can come up with other examples. So let's just use this to get a terminology and then to also see how we abstract the flow network into a simpler drawing. So here, let's just give me maybe a sort of a flow of liquid. So we're kind of imagining a piping system. Maybe it looks something like this, and it looks like this. Okay, so what we're imagining is we have the external world to our system over here, and we have 25 liters coming in, and we measure or we observe there's 10 liters coming in here. There are 15 liters coming in here. So that means that, of course, there must be 25 liters flowing through this main branch here. And then I've decided that maybe there's 5 liters coming out here, 12 liters coming out here. And that, of course, then means that there must be 8 liters coming out here. And there's 25 liters coming out. So in this world that we're going to deal with, we're assuming that in the system that we're looking at, that there's not a source, like there isn't somewhere where liquid is being, injected in somewhere, and there isn't a sink, like there's not a hole in the pipe and liquid is leaking out. Okay, so that kind of a situation, we will simplify the drawing, and we'll draw it like this. Okay, this makes more clear what are the nodes and what are the branches. So we call these things here nodes. And then we call these guys, all these things, branches. Okay, and then in this example, we would put a 10 here, 15 here, and we indicate the direction of the flow with an arrow. So we've got a flow here of 25. Here we have a flow of 5, 12, and 8. Okay. So we've obviously got the nodes, we've got the branches, and this could indicate a variety of different physical situations. Okay, most of the flow networks that we look at will satisfy these properties. There's one directional flow. So we're not sometimes having water flowing in one direction and then flipping some sort of a switch and it's flowing the other way. We're analyzing ones where at any particular moment anyways, the flow is going to be in one direction. We don't have back eddies or something like that. There's flow conservation. It means that when you come into a node, like let's just take a look at that one right there, 50 liters is coming in and 50 liters is going out. We're not losing anything and we're not injecting anything. And then there's flow conservation. That one is telling us that in this example, there's 100 liters coming in, and over here, there's 100 liters going out. So in a typical problem, what we have so far, we've just sort of given a demonstration of what a flow network is and what the principles of it are. We don't actually have any problem to solve. Typically what happens is you have some flows are known and then other flows are unknown, and you want to identify what those unknown flows are. So the key point here is that we've abstracted the physical situation firstly into this flow network. So the flow could be numbers of cars. It could be, let's see, numbers of cars. It could be, let's think, liters of a liquid. It could be current in an electrical circuit. So this is what we like to do in mathematics. We like to have some sort of a problem. Actually, we like to have more than one type of a problem. And then we like to abstract the problem and identify that we have the same problem in many different contexts, learn how to solve the abstract problem, like here's a flow control network, and then we can apply that to whatever physical situation we actually do end up having. And that's where a lot of the value of learning something comes from, is that you can apply it potentially to many different situations. Okay, so here we are in what's an actual problem. We're going to look at a network flow problem. This one is showing, was telling you, is showing you current flowing in the directions indicated, and you want to find the unknown current. Okay, of course, it doesn't have to be current. It could be water, it could be something else. Okay, so we have unknown flows. That's the first thing to notice. We have unknown flows. There they are there. These are unknown flows. Okay, it was something is flowing through that branch right there, X1, etc. So there's unknown flows, and we can assume a direction. Why? So if you have an unknown flow, you can simply assume a direction. That is because if after you solve the problem, the unknown flow comes out to be a negative, you realize, oh, it's actually in the other direction. Like the mathematics will sort itself out and will tell you whether your assumed direction was incorrect, at which point you just change it to the opposite direction if you get a negative number. Okay, so if negative, flow is in the other direction. Okay, so how are we going to go about these problems? There's an algorithm here. Let's say what it is. Assign variables to unknown flows. That's already been done in our drawing. Assign variable names to unknown flows. Okay. Use conservation of flow at each node to generate as many equations as there are unknowns. Okay, so if in this case, we have 4 unknown flows, I'm expecting that we'll be able to generate 4 equations. Okay, we don't expect there to be no solution, but it is possible. I mean, somebody could set up a flow network where it's simply impossible to find unknown flows that satisfy the flow conservation at every a node. So if you can come up with a situation when you solve it, it says the mathematics is telling you, oh, this is not a solvable. This one has no solution. You might have made an error. I would be more inclined to check my work when that came up to make sure, but it is definitely possible. We don't expect it though. We also don't expect an infinite number of solutions, but again, that is possible. Depending on how the unknowns are, which ones we don't know and which ones we do, it may be possible for more than one possible configuration to satisfy the known flows and all the other rules of the flow network. So should that happen, you can express that as there's an infinite number of possibilities here. Here's one, this one, and then somebody can be showed what is at least one potential solution with numbers. Okay. So the next thing that we do is, well, those are really the two steps. We've assigned the variables, and now we're going to use conservation of flow to generate the equations. I guess step 3 is then solve the equations and get the solution. Okay, that is the part that you've already learned how to do. So we've already learned how to do Gaussian elimination in order to solve a system of linear equations. So the interesting part here is going to be getting those equations. So we'll take a look up here, and what we're going to do is label the nodes. I'll just label them here like this. So we're going to label the nodes just so I can indicate which equation I'm generating from which node. So I'm going to label the nodes here, 1, 2, 3, and 4. And then I'm going to use each one of those nodes to generate an equation. So let me use node number 1. I'm looking at node number 1, and I'm basically equating the flow into the node with the flow out of the node. That is the flow conservation at the node. So that means that the flow x4, which is coming in, has got to be equal to the flow going out, which is 100 plus x1. Okay, same thing on node 2. Let's take a look about what the flow coming in is. The flow coming in is x1 is coming into the node, plus 500 is coming into the node, and what is going out? X2. I look at 3. What is coming in? Let's see, that is x3, and what is going out is 300 plus x4, and then node 4, what's coming in? X2, and what is going out? X3 plus 100. Okay, so here we have now 4 equations and 4 unknowns. Great idea for you. Stop the video right now, set this up into an augmented matrix, solve it, and see if you get the solution. And then you can turn the video back on and go through it at double speed and see if you're right. Or if you weren't able to do it, then go more slowly and see where your solution is different from mine and what you can learn from that. Okay, so I'm going to just I'm going to do this relatively quickly. We're just going to rewrite the equations into a format that makes it easier to form the augmented matrix. These are the same equations as on the left, but just rewritten. Okay, 4 equations, 4 unknowns. Then I can form the matrix. And so that is from the first equation, I'm getting this one, minus 1, 0, 0, 1, 100, and 1, minus 1, 0, minus 500, and 0, 0, 1, minus 1, 300, 0, 1, minus 1, 0, 100. Okay, there we are. Now, this really, in some sense, is nearly a solution, in my opinion. We've analyzed the problem. We've developed a system of linear equations. All we have to do now is the algorithmic Gaussian elimination, and we've got the solution. So this is something that if you can do already very well, then really just do it quickly and ensure you're right, and move on to the next example. If you need a little bit more practice with Gaussian elimination, then go through this. I'm going to do a little bit more quickly maybe than I otherwise would. And of course, in a more real life example where we may have like 15 or 20 equations and 20 unknowns, then this matrix would be entered into a programming software like MATLAB or Symbolab, and we would simply ask for the solution. In fact, given that we're going to be doing some computing assignments, that is also a good exercise for you to do. Take this, figure out how to enter it into MATLAB as a AX equals B system of linear equations, and ask MATLAB to tell you the solution. Make sure that agrees with my solution and maybe your solution by hand. All of these things are good exercises for you. The more work that you do, the better. Okay. All right. So let me just do this here then. We've got the thing. My first row operation is going to be, I'm going to multiply row 1 by minus 1. So row 1 is going to become minus 1 times row 1, giving me this. Okay, and then I am going to, this symbol here means I'm going to generate a matrix with equivalent solution set. So each one of these matrices that I write down has the same solution set. That's what that little symbol is. I'm generating a new matrix, but it has a equivalent solution set. Okay, so what I'm going to do, I'm going to take R2, and that R2 is going to be replaced by R2 minus R1. Okay, and that will give me the following: 1, 0, 0, minus 1, minus 100, 0, minus 1, 0, 1, minus 400, 0, 0, 1, minus 1, 300, and 0, 1, minus 1, 0, 100. Okay, we can now see that we are done with this row. This one is done. And that's because we've got all zeros here. So now we're now going to focus on, next thing we're going to do is focus on this row here. And our idea is to make both of those entries there to zeros. And in fact, we want to also make this entry to a 1. Okay, so I'm going to first do that. I'm going to multiply. I'm going to multiply R2 by minus 1. This is a time-consuming procedure to do by hand. Okay, next operation, I'm looking at wanting to make that guy into a 0. So what I'm going to do is take that fourth row, and I am going to replace it with R4 minus R2. Now is a good time, if you're not, if you're thinking, why are you allowed to do this and it doesn't change the solution set, is to look back and review the elementary row operations and why they don't change the solution set to a system of linear equations, because we're always going to be using the 3 elementary row operations in order to do this. Okay, now we're done with this one, done and done. Why am I saying that? Well, because I've got a leading 1 in both of those positions, and I've cleared these guys to 0 below. And so now what we're going to do is we will be looking at the third row, and we'll be, notice, like we're saying, great, it has a leading 0. The third row has a leading 0. So now the idea is to get that guy to be a 0 right there. And so how am I going to do that? I'm going to add row 4 and row 3. So I'm going to take row 4 and change that to row 4 plus row 3. Other thing to notice is you may have chosen a separate, or I should say a different set of row operations than I did. That's perfectly fine. There's multiple ways of doing this, and some ways are much easier for the arithmetic and much faster. So a little bit of thought should be put into your row operations. Don't just sort of blindly hammer through. You could say, well, maybe if I exchange 2 rows, the whole thing is easier. I don't introduce fractions, or I don't have to do as many row operations if I do. So there's multiple ways of doing it. So experience is good for that reason too, because on a test, you're not going to want to go down the slowest path. You're going to want to be efficient. Okay, so I'm on row 4 plus row 3. That gets me this guy here, 1, 0, 0, minus 1, minus 100, and 0, 1, minus 1, whoops, 0, 1, 0, minus 1, 400, 0, 0, 1, minus 1, 300, and a full row of zeros here. Okay, so we're now in a situation where we can stop. And interestingly, what has happened here is this row here is telling me that X4 is free. X4 is free, So I actually have more than one solution to this problem. Okay, I'm going to then, therefore, because X4 is free, I will assign it a parameter. That is X4 is equal to T. Now I'm looking at the back substitution, and I'll just go row by row. So I've got X4 is equal to T. That tells me that X3 is equal to 300 plus T. then I'll go with this next row here, and that tells me that x2 is equal to 400 plus t. And then finally, the first row there is x1 is equal to minus 100 plus t. So I can now provide you with a variety of different solutions here. I will choose one. So I'm going to say let t equals to 50. So sometimes when you end up with a variety of solutions, you might have something where you want to have whole numbers only, at which point you would select a parameter to hopefully, if it's possible, to hopefully give whole number solutions. So in this case, it doesn't matter, but I'm going to just let t be equal to 50, and then that allows me to calculate all of the variety of flows. That would then end up giving me x4 is equal to 50, x3 is equal to 350, x2 is equal to 450, and x1 is equal to minus 50. So this one is negative, so it means that the direction of flow on the first drawing is actually going to be the other direction. So I'll just redraw the network here. It looks like this. Great symmetry on this. What am I doing? I'm putting too many guys coming out. Let me try that again. Let me redraw the network. Got excited about the symmetry of it and made a mistake on the drawing. It's still nicely symmetric though. There it is. Only one coming from each node. So these are the nodes here like this. We had the known flows here of 100, 300, 500, and we have directions associated with these flows, that direction, and we had 300 hit it out over here and 100 hit it out over here. And then we had this one here. This was x2, which we've identified to be 450. This one here was x3, which we've identified to be 350. This one here is x4, which we've identified to be 50. And then this one here is x1, and you'll notice I'm changing the direction of the arrow from the original. So that is now 50 in that direction. Now you should do a quick spot check when you do this. So you should take a look at the nodes and see, is everything good? So I take a look at this node and I'm thinking, okay, 500 in, does that equal 450 plus 50 out? Yes, let's just similarly do this one. We've got 350 in, coming in here. Does that equal 50 plus 300 out? Yes. So you can quickly check your solution. That will alert you to possible direction problems or possible arithmetic mistakes in doing the Gaussian elimination, which is extremely easy to do. So easy to make a mistake with the arithmetic during Gaussian elimination. Okay, next type of example is the balancing of the chemical equation. You need to know nothing about chemistry in order to do this. All you have to understand is that you're being told if you take this chemical and you react it with this chemical, you get this compound out plus this compound, right? I mean, many of you probably already know what these things are, but it honestly does not matter if you do not. Okay, so what is telling you is this for reasons of chemistry, this is what happens. Now what you want to do is balance this, which means that you want to have this, if you look over here, you want to have the same number of hydrogen molecules at the start as you do at the end. So there should be the same number of hydrogen molecules on either side of the equation. There also should be the same number of sodium molecules on each side of the equation. Right? So nothing is being created or destroyed during the chemical reaction. It is that it's a complete chemical reaction. Everything on the input is being used up and producing output. Okay, so that is all the chemistry that we need to know. So what do? We assign variables to balance the equation. I'll show you how that works in this case. Assign variables, just like we did in the previous flow control case. And then we are here going to be thinking that values we expect, this is what we expect, or it's in some sense forced by the kind of problem we're dealing with. Values should be positive. Okay, we don't have a way of interpreting -3 hydrogen molecules. That doesn't make sense. There's not kind of an obvious, it's not like flow where it's like that, oh, that's the other direction. No. So we're expecting the values to be positive, and we are expecting the values to be integers. Okay, it also doesn't make sense to have 1.5 hydrogen molecules. It's okay to have 1.5 liters of water, but not 1.5. So we're expecting this. So this constraint right here is not a mathematical constraint. It is a constraint from an understanding of the underlying physical situation that we're trying to analyze. We just note that as we're going along. So what do? Then let's assign our variables. It means we're going to have x1 of sodium hydroxide plus x2 of hydrogen. Is this I'm not even sure. That might be it's not an acid. I don't think sulfuric acid, but hydrogen sulfide. I don't know. I'm not sure of I can't remember my grade. Last time I took this was when I think I was in first year university, and that was a seriously long time ago. Okay, of this compound here. There we go. And then we produce some amount of this guy here. And water. I've got the water. I'm onto the water. There it is. Okay. So we are just saying how much of this one plus how much of this one equals how much of this one and how much of this one. So we've got 4 unknowns. And so we're thinking, of course, we need to get 4 equations. And what are we going to do? How are we going to do that? We want to equate the number of atoms of each particular type on both sides of the equations. So let's for example, take a look at hydrogen. Okay, we have some number of hydrogen from this term right here. That's going to be x1, and there's 1 of them. So x1 times 1. And then we look here, how much hydrogen do we get here? We get 2. There's a 2 there. So we get, for every x2 that we put in there of that guy, we get 2 x2 hydrogens. And then on what happens on the output, there's no hydrogen there, so we have no x3 term, and then we get 2 x4. So we write out the equation for hydrogen. We write it out for sodium. Again, now's a good time. Now you've seen this example with hydrogen. There's 3 other things. There's sodium, sulfur, and oxygen. So what you could do is stop the video and just write out the other 3 equations. Then check that that you did it like I did. Okay, here, so we go with the sodium, same thing. I'm going to get right here. There's 1 sodium, so I've got x1. There's no sodium here, so there's no x2. And then over here, there's a sodium here, 2 of them, 2x3, and no sodium here. So the sodium is done. I go through next. This should be now fairly quick process. Sulfur. I see no sulfur in the first term here. I see sulfur there. I've got 1 of them times x2. So the sulfur is 1 times x2, and that is equal to the sulfur is showing up here with a subscript of 1. So we've got here just x3. And finally, the oxygen. That gives me x1 from the first term. Oh, and then we have something a little bit more exciting, 4x2. That 4 is this guy here, 4x2. And that is giving me 4x3 plus x4. So the 4x3 is here, 4 times x3, and then 1 times x4. Okay, 4 equations, 4 unknowns. Same thing's going to happen, right? We're going to form the augmented matrix, and we're going to use Gaussian elimination. Great time to stop the video, do it yourself. Okay, it's way better to do stuff yourself than watch somebody else do it. Okay, here's the augmented matrix. There it is. Okay, we notice in this application, all these guys are 0. So just, I mean, things should just kind of pop into your head. So we notice, hey, so just in the back of our mind, we're like, oh, this is a homogeneous system. All those guys are 0. We just remind ourselves of that just as sort of a review. Okay, now I'm going to do the same thing. I am going to use Gaussian elimination to find the solution. So the first step, of course, is going to be I want all of these guys here to be zeros. And I can see that I can do 2 of them at once. I can take R2 and replace it with R2 minus R1. At the same time, I can take R4 and replace it with R4 minus R1. Okay, be careful. You cannot change one of them and then use the changed one to do the other one. But these are independent operations, so I can do both of them at once. So I'm going to generate an equivalent matrix that will have the same solution set that looks like this. Okay, now I want to take, and I've got the leading one here, and I've got all the zeros here. So I'm moving on to this position right here, trying to get a leading one there with zeros below. I could swap rows 2 or 3, or I could multiply row 2 by minus a half row 2. Either one is possible. So there's a couple of possible ways. I, for whatever reason, chose this one, R2 being replaced by 1/2 R2. I probably would not have done that if that generated fractions. In this case, it doesn't, so I'm going with it. In fact, it makes the numbers smaller, so that's I like that. Less likely to make an arithmetic mistake with small numbers. Okay, now I'm going to get the 2 zeros here. That is going to be a matter of taking R3 and replacing it with R3 minus R4, and taking R4 and replacing it with R4 minus 2R2. And I'm going to generate the equivalent matrix. Here it is. 1, 2, 0, minus 2, 0, 0, 1, 1, minus 1, 0, 0, 0, minus 2, 1, 0, 0, 0, minus 6, 3, 0. Okay, now we're in the situation where we've got leading one here, zeros below here and here. We move on to looking at this guy right here. We're wanting to make that into a leading one with zeros below. Now, how am I going to do that? I am going to take R3 to be minus a half R3. And I'm also going to take R4 and replace it with R4 minus 3R3. Okay, I'm doing this operation with the original R3, not the new R3 I'm producing. Okay, so I want to do them both at once. And I'm imagining myself doing this operation in some sense, writing out the matrix again, and then doing this. I'm just too lazy to write it out. So just be careful when you see this being, 2 of them being done. You are using the original R3 right here, not the new R3. Okay, that allows me to write this out in one step. If that is slightly confusing, then stop the video, do it yourself, one row operation at a time, and see that you get the same thing that I got here too. There's a lot of value actually in doing something in gory detail the first few times you do it, and then from that, using your experience to realize what shortcuts you can do, right? Because you don't want to accidentally think, oh, this is a nice shortcut, but it's actually mathematically not allowed. So what you want to do is maybe do it in detail the first few times until your experience allows you to see exactly why some things are an allowable shortcut and others are just frankly an error. Okay, so that original row 3. Okay, here we go. 0, 1, 1, minus 1, 0, and then this nets me this here. 0, 0, 1, minus a half, 0, 0, 0, 0, 0, 0. So again, I have a situation where I have a free variable. It turns out, in fact, it's the same variable. It's x4. So that tells me there's infinite number of solutions. So let's look like why I can stop. I've got a leading one in all of the rows, and I've got zeros below, I guess in all of the rows possible, and I've got zeros below the leading ones, and then at the bottom, I've got a row of all zeros. So I have completed the Gaussian elimination. You'll notice I almost never do the Gauss-Jordan elimination. I stop at the end of the Gaussian elimination of the Gauss-Jordan procedure, and then I simply use back substitution. I find that way faster. So again, from the bottom row, I'm identifying that x4 is a free variable. Then I look to the next row up, and I see that x3 is 1/2 x4, which is, because I've identified x4 as t, is 1/2 t. I head up to the row above, I get x2 as minus 1/2 t. Hang on a sec. Minus 1/2 t. Oh yeah, that's because here is x4. Oh, x3. That is x3. Sorry, that's x3. This right here is x3. And then I have plus t, that is x4. And those two of those together is 1/2 t. And then I follow that up here with this first row. I get that x1 is equal to minus 2 times x4, which is 1/2 t. That gives me t. Oh, sorry, I forgot to add in x2. So that is 2t. And that gives me a total of t. Okay, there we go. Perhaps I should have wrote those out in a little more detail. If it's confusing, if this was a little bit confusing, take this and write out the solution set very carefully and then compare it with this, because this is what I got at the end here. We have a solution vector and it looks like this. Okay, now I know from my previous thinking about the problem that I expect that all of these values, x1, x2, x3, and x4 will be integers, because I can't have half of an atom. So I choose t equals to 2, which is the smallest number that gives me integer value solutions. Okay, and also we can see that this is going to give me all positive solutions. If I was unable to choose a value of t to make them all positive, then I would declare that there isn't a solution to this problem. Even though there's sort of a mathematical resolution, in some sense, the fact that it can't be sort of applied to the situation under concern, I would say, okay, mathematically these numbers all work, but we doesn't make sense for us to have negative hydrogen or something like that. So therefore, there is no solution to this problem. In this case, I can choose t to make them all positive and to make them an integer. And so that gives me that I then use this. I get the values of x1 through x4, and it allows me to write out the balanced chemical equation that you need 2 sodium hydroxide plus this guy here, giving you this guy here plus 2. So that now this is balanced. It would be balanced if you choose 2 equal to 20 for that matter. It would just be that all of these would be larger numbers. You might as well, in this case, it's typical to provide the smallest numbers here that are integers that balance the equation. Okay, so that's the chemical balancing problem. What's interesting from the mathematical perspective is we had a network flow problem. We have something now totally different, balancing a chemical equation, but we see that actually after we analyze the problem and turn it into mathematics, they are the same problem. And we have our Gaussian elimination in order to solve that. Okay, here's a more mathematical problem. This is the problem of polynomial interpolation. So this will be our last example in this lecture. And what polynomial interpolation means, what this word means, interpolation, is that we have some amount of data like that. Okay, and we want to find a polynomial that goes through all of the points. It's not close or anything like that. It's actually going through. So we've got some number of points, and we're saying, please find us a polynomial that's going to go through our first point, go through our second point, go through our third point, and go through our fourth point. And then typically what you're doing in this kind of a problem is you use that polynomial to estimate what the what the value would be here, to give some sort of a prediction. You have measured data at those little blue crosses, and then you want to understand, okay, what would we basically expect at places where we don't have measurements? That is in between the data. We don't generally use interpolation outside of it's called extrapolation. So interpolation is when we're taking the data and we're fitting, in this case, it's polynomial interpolation. So we're going to fit a polynomial. We're going to talk about the degree of the polynomial in a sec, but we're going to fit a polynomial through, and then we're going to be able to use that polynomial to calculate the values where we don't have measured data, say. Okay, so that we're going to rely on a theorem here. That is that if we have n points in R2, that where the x coordinates are different for each of those points, that there's a unique polynomial of degree n minus 1 whose graph goes through all the points. Okay, so we have n points, and we'll be looking for an n minus 1 polynomial. Let's just see a couple of examples of that. If we have 2 points, what do we expect? We expect a line, right? We know that a line goes through 2 points. So here we have 2 points, and what we want to do is find that line. That's 2 points, and so we're going to be looking for a polynomial that looks like this. It's of degree 1. We don't usually write the 1 there, but there is a 1 there. So that is of degree 1. So we see that we have 2 points, and then 2 minus 1 is 1. We're expecting a degree 1 polynomial. You'll also see that we've got 2 things that we need to find. So before you start one of these problems, you sort of make sure that it makes sense what it is that you're trying to find given the data that you have. Let's just do another one of these things. Imagine we have 3 points. They look like this, say. Okay, so we have 3 points. The x coordinates are different. So then what we're going to do is we're going to be looking for a polynomial that is of degree 2. Right? 1 less than the number of points that we have. So we're looking for a polynomial that goes through these points. It's supposed to go through the points. It should be a second degree polynomial that looks like this. Okay. It is a second degree polynomial, a quadratic. And you'll see that there's 3 things that we need to figure out. Okay, so let's now try this out. We're going to find the polynomial interpolation of these 4 points. Okay, it's 4 points. So what do we expect? We expect a polynomial, because we're doing polynomial interpolation, polynomial of degree n minus 1, and 4 minus 1 is 3. Expect a polynomial of degree 3. Okay, so then let's just make sure we understand the meaning of each one of these points. The point means, that point right there means, what does this mean? Means when x is equal to minus 4, then y is equal to minus 2, right? We always write our points like this, x, y. So it means for this polynomial that we're trying to find, it must be the case that when we stick x to be minus 4, then y will be minus 2, because the polynomial has to go through every point. So it has to, for the first point, it has to be that when x is minus 4, our polynomial will give us the result y is minus 2. That's what we do to generate the first equation. So we have a polynomial of degree 3 looking like this, a0 plus a1x plus a2x squared plus a3x cubed. There it is. And we're trying to find a0, a1, a2, and a3, because that tells us exactly which polynomial of degree 3 it is. So the idea is we're trying to find a0, a1, a2, a3. So we are going to generate one equation from each point. So let's take a look at the first point. Talking about that point, we had already established, point 1, that is going to be minus 4, 2. And we've already established that y has to be minus 2 when x is minus 4. So now I'm substituting in the x for minus 4 into this side over here. Okay, now I look at point 2. That is the point -2, 1. And I do the same thing. Y has to be 1 when x is -2. Okay, good time for you to stop the video, generate the equations for the next 2 points. Point 3, which is this guy here, and point 4, which is this guy here. Okay, so you just saw 2 examples of how to do that. Just stop the video, generate equation 3 and equation 4. This will be a good check that you understand what to do. And this is what I got doing that. The y value is -3, and substituting the x value as 2, I got this. A0 plus 2a1 plus 4a2 plus 8a3. And I got here in this point 4 where the y value is 3, and I'm substituting in x is equal to 4, and I get this here. Okay. All right. I feel now happy. I've got 4 equations and 4 unknowns. Now, what I'm going to do is I am in a position where I have now taken a completely different type of problem. So we first ended up with 4 equations and 4 unknowns looking at flow control. And then we ended up with 4 equations and 4 unknowns looking at balancing a chemical equation. Now here we are, 4 equations and 4 unknowns in this situation looking at polynomial interpolation. So after we have abstracted from the problem, we've ended up with exactly the same mathematical problem. We're just repeating ourselves over and over again. So knowing how to solve this type of mathematical problem has allowed us to solve actually what look on the surface as very difficult, very different problems. So again, good point, stop the video, and then you've got 4 equations, 4 unknowns. Go through solving this, do it by hand, and then go and figure out how to enter this into MATLAB and get MATLAB to tell you the answer. Now you can check your by hand work, you can turn the video back on, and you could see if I'm right, because if MATLAB says, if you've entered it right into MATLAB, and that's different from me, I'm going to believe MATLAB, and then see if you did it by hand. Just practice. Okay, so I am not going to go through this one myself in gory detail. I'm going to write here what the augmented matrix is. Okay, so I'm entering these equations into the augmented matrix. It's pretty ugly, actually, I think, to do this one by hand because of the numbers. You can see that's what's going to happen. Well, you can not for sure, but you can see likely what's going to happen is you're going to get fractions. I mean, you have the numbers on the left don't look too bad, but when you have 3s and then you also have 16s, you're like, uh-oh, right? Might end up with some problems. So in terms of arithmetic, not difficult, but just hassle. Okay, so Gaussian elimination. Gaussian elimination, you're going to do that by hand and or with MATLAB. Make sure you can do that. Try, and then right after the Gaussian elimination, you do back substitution. And if all goes well, and all went well for me, we will agree that this is the answer here. Please check. There it is. I got these answers. I got this system to give me this answer here. Okay, there it is. What does that tell me? That tells me that this polynomial, this guy right here, okay, it tells me that this polynomial right here goes through all 4 of the points. You could check that, right? You could take that very first point that we talked about, -4, -2. Okay, you could confirm by plugging in -2, constant term, by plugging -2 in here and then taking -2 there and squaring it, and then taking -2 there and cubing it, and adding these all together, that you would get -4. So you can definitely check that. So this is now 4 equations, 4 unknowns. We solve it. We get the coefficients of that third degree polynomial. Now that polynomial goes through the points. Now we can use this polynomial to calculate the values at X for which we don't have that data. That's it. There's 3 examples of how to go ahead and do this. And here is some exercises for you to try out, a couple of network flows and polynomial interpolation, and then balancing some chemical equations. And this might be a little bit time consuming, but the more you can practice, the better it is. Okay, I'm done with this, and I'm going to be back with the next lecture shortly. Thank you.